This video will be on section 6.2, applications in business and economics. But really in this section, we'll be looking at one problem that in some ways you've worked on before, but kind of an unrealistic type of way it's been worked on, and now we're going to make it more realistic. And they're both related to continuous income streams. One is the total income for a continuous income stream, and then the other is the future value. But we're pretty much only ever interested in the future value. You can kind of think about if you're investing some money in something and then you put some more money in it over time. That's the continuous income stream part, is doing it over time instead of just depositing one amount and then asking yourself, what is it going to be in the future? All right, so the idea of what is total income for a continuous income stream. Well, building on the ideas of area between curves and definite intervals, we know that if f of t represents the rate of change of a quantity. So once again, think about an investment, think about measuring how much it increases or decreases over time. Then the quantity produced, so the amount gained, we saw a word problem where we talked about the increase of cost over two production values. The amount gained or lost from t equals a to t equals b is given by the definite integral from a to b of your total of your income rate of change, f of t. To apply this in a more specific manner, if f of t represents the rate of flow of continuous income stream, then the total income produced from t equals a to t equals b, don't have the t part, is given by the same thing. Right, so just kind of to understand a little bit the idea here, we won't be doing just the total income because the hope is that you're investing and not making a 0% return. You're increasing your money as well. But the idea is if you invest $4,000 per year for 20 years, but make 0 interest, which would be really unfortunate. Now, you can just multiply 4,000 by 20 to get the 80,000, but another way to get it is we could integrate from 0 to 20 the continuous income stream 4,000 dt. And when you integrate this, since you're integrating just a number, you get the number times t. We evaluate from 0 to 20, and then we plug that in. And when we plug in the 0, sorry, I'm running out of room, but when we plug in 0, that's just 0. And then we get exactly that 4,000 times 20, which is 80,000. Right? So we don't really worry specifically about the total income because we're not trying to make 0% interest in our investments, but that's the starting point. Right? The hope is that you will make some money, and it can be approximately thought of as continuous income stream that's compounded continuously as well. So what we'll do is kind of take this thing and add in the PERT formula somewhere. Right, so recall that if an investment compounded continuously with principal value P, so the amount we invest initially, the annual rate of change R, then the future value A, T years into the future is given by that PERT formula. The reason why those word problems back then are not very realistic is that, it wouldn't be a smart idea to invest money, have it grow in some account, but then never invest some more because you're losing out on money. If it's growing, you would want to put more and more in it, probably as much as you possibly could every time you're allowed to, depending on the type of account. So that's not a very realistic thing, but what if we thought about the question and said, hey, what if we do have a continuous income stream that is being compounded continuously, and we invest $4,000 a year into it, like above, but we are making 3% interest. Well, then the way that works out is kind of like adding on, it's going to look like multiplying on the PERT stuff here. The initial formula looks pretty confusing, and I have a long chain of equal signs because the last one is the real one that we're really going to use. So it says, by supposing instead that money is added in the continuous income stream f of t, and we want to know the future value FV after capital T years. So this is an important distinction between the PERT formula and this formula, is that T is the after T years, the lowercase t is our variable. Then the future value is given by f of v. So initially what you would do is you would take your $4,000, multiply it by e to the RT. So this is like your P in PERT, your initial amount. You're multiplying it by e to the RT. But you have this little adjustment here because this is going to give you the amount of years to grow. So if you invest for 30 years, then when you're at time 0, you're at your initial time as 30 years to grow, and your exponent would be 30 minus 0, which is 30. So that's where the capital T minus lowercase t comes from. But what the formula that's easiest to remember, because we would go through this simplification every time, is right here. Right, so just to condense it, I'm going to rewrite it below. The future value equals e to the r capital T, integrating from 0 to t. Then we have f of t times e to the r lowercase t dt. Right, pretty messy formula. Let's point out all the different variables. R is just our interest rate in decimal like before. F of t is like our PERT, is the continuous income stream. You know, how much are you making per year, and that sort of question. The capital T, this is very important. The capital T is how long you will invest in years. And then the lowercase t is your variable. Right, the reason we know that's the variable is because also you have dt here. So when we plug in our formula here, we will leave t alone. That's the variable that we will be integrating. And we won't plug in until after integrating. Right, but once again, we're really just combining the PERT thing with the continuous income stream that I explained above, the total income, to get this formula. Right, but this formula for sure, the one thing I recommend is that when you do it, kind of remember PERT, because you have e to the RT in a couple spots. And then remember that the f of t is like your p, and it should help you memorize a little bit. But every question in this section is either just an integral that already looks like this, so it's not going to be a word problem, or it's going to be a word problem, and you're going to use this formula at some point. So before I even do this problem, I'm just going to write it down. F of v equals e to the r capital T, integrate from 0 to capital T, then f of lowercase t times e to the r lowercase t negative r dt. Okay. Right, and I guess I should have explained something here. Why can the e to the rt be outside of the integral? Well, it doesn't have a lowercase t in it. It doesn't have our variable in it. So we are allowed to bring anything. This is just going to be a number. We can bring it out. So that's why that's out front. All right, well, let's go ahead and read our question, see if we can identify everything we need to plug in. We're going to plug in for an r, we're going to plug in a capital T, and we're going to plug in an f of t to these equations. Right, like I said, the lowercase t is what we're going to be using as our variable, so you won't plug in for that. All right, so this says, starting at age 25, you deposit $2,000 a year into an IRA account for retirement. Right, pretty much anything with a number. The age here doesn't necessarily matter, but that part I underline is going to matter. It says treat the yearly deposits into the account as a continuous income stream. All this means is use the formula for our future value for the continuous income stream. And it says, if money in the account earns 6% compounded continuously, it's got to be compounded continuously, otherwise this formula wouldn't work, but it will be in our problems. So our R is actually right there, 6%, which as a decimal is 0.06. The question is, how much will be in the account in 40 years? This is how long it's going to be invested, so that is what capital T means. T is 40 when you retire at 65. So it's asking for the future value. And then just because it's interesting to know is, compare this to how much you would have if you didn't invest. How much of the final amount is interest? So we'll have to do this at the end after we get the future value. Right, so the thing that I highlighted at the beginning, the $2,000 per year, is our continuous income stream. That's the income that we're placing into the account. It's just $2,000. Now it's possible they can give you a function here with a t or something in it, or an e of t, but this one is just a number. All right, but what we're going to do, plug these into our formula here, and then we're going to give ourselves temporary amnesia and just do the integral. Because if you try to overthink this, I think it becomes more confusing. All right, so R is 0.06. Capital T is 40. Integrating from 0 to our capital T, which is 40. F of t is 2,000. E to the negative r is 0.06. And then t, well, that is our variable, so we aren't plugging in anything for lowercase t. Now, what I recommend is just simplifying here, whatever you can. What we can simplify here is we can multiply the exponent here to make that simple, and then we can also bring out the 2,000 since it's just a number. So we got 2,000 e 0.06 times 40 is 2.4. Integrating from 0 to 40, and we have e to the negative 0.06 t dt. Right. So every single problem that you work in this problem, you're probably going to end up integrating something that looks like e to the some number times t. Now this is something you have to use the chain rule for, substitution for, but I'm going to give you a formula because it's so common in this section that it can make it a little bit quicker for you. The formula is for integrating 0, I don't even need to put numbers on it, e to the at dt. So what do we get if we multiply e, or we integrate e to a number times t? So this is what you'd have to do every time if I didn't give you this formula. We would use substitution. We would use u equals a to the t because the exponent is not just t. Then du, the derivative of a times t is just a because it's like 3 times t, the derivative would be 3 dt. And then we would divide by the a on each side and get dt equals du over a. We would plug them in. Once again, I'm just doing this on the side to the problem here, and I'm going to use the formula for this and wherever else it pops up. We got e to the u power and then dt is du over a. Once again, a, just a number, so I can bring it out. We get e to the u du. And then we can integrate e to the u, which is just itself. I'm not writing the plus c. I guess I should. But when there's numbers on it, of course, we don't need the plus c. And then the last thing to do is plug back in what u is, which is a times t. All right, so what our formula says here, the way I'm going to use it is if we integrate a number, e to a number times t, or x, it doesn't matter what the letter is, gives you that thing, but then you divide by that number, right, that a here. Right, and instead of going through and doing substitution on every single one of the problems in this section that are all going to pretty much look like this, we can use this shortened formula. Right, so when we integrate, e to the negative 0.06t, we get e to the negative 0.06t, we get itself, divided by negative 0.06, that number. Okay. And then evaluate. Don't need a plus c here because we have a definite interval. We're evaluating from 0 to 40. Now, do what we always did before. What I recommend is, since you have two parts with e and two parts without e, simplify the parts without e. So you got 2,000 divided by negative 0.06. And that doesn't simplify a lot, but it's negative 100,000 over 3. Then we got times e to the 2.4, then times e to the negative 0.06 t, and then we'll evaluate. So I just simplified it a little bit. Now I'll evaluate, plug in 40. Subtract and then plug in 0. 1, 2, yeah, that's the right number, over 3, times e to the 2.4, times e to the negative 0.06 times 0. Right, so I plugged it in. Since I only have one term here because they're all multiplied, I didn't need an extra parentheses. Just going to change that double minus into a plus now. And then the last thing I would do, and then I'll use my calculator. Since this is a word problem dealing with business applications, we don't want a number that's not a nice decimal that we can round and understand. So you can type in the whole thing in your calculator now. I'm just going to do one more step before I do that. So our exponent here, negative 0.06 times 40 is negative 2.4 plus and then e to the 0 is just 1. So that'll be a little easier to type in. But now I'll type it in the calculator. Right, the first thing you'll notice that the exponents here, with exponent rules, it should come out to be pretty easy answer. It should just be this number. We'll see how that works. So you got negative 100,000 divided by 3 times e raised to the 2.4 times e raised to the negative 2.4 and right? We can leave it as a decimal because we're trying to understand the number here. So we got negative 33333.33 plus, and then when we type the other one in, we got 100,000 divided by 3 times E raised to 2.4. I don't need to multiply the 1. I get 367,439. 2127. And go ahead and just add these together in the calculator now. I'm going to take my last numbers since it's added and then subtract that 3.333. And we get $334,105.88. That is the future value of this investment. Right, now do keep in mind that one of the reasons this problem took so long, I derived a formula for you that you can use. And also I probably went a lot slower in the evaluation process just to show every step than you might on your own. But the integration step was pretty short. It's just reading the problem, figuring out what you're going to plug in and do that. And then kind of like letting it fall through. So the future value of the investment is this. We also want to know how much of the final amount is interest. Well, the interest would be the future amount minus the amount if not invested. Right, so the future amount we know it, we just figured out. How much would we have if we did not invest our money? Well, we invest $2,000 a year for 40 years. So that's a pretty simple calculation. If we did not invest, we'd have 2,000 times 40, which is 80,000. Right. Technically, if you had a function in here that dealt with t, so the amount you deposited depended on the year, then you would have to do the integration. But there's not any problems in the homework like that. So just if you're trying to figure out how much of the final amount is interest, you've done almost all the work. With the future value, then figure out that calculation, and then we'll compute it. So I still have that number pulled up. Just going to subtract off 80,000, and we get $254,105.88. Right. And that shows you how crazy, how crazy your investments can be if you are, I guess, lucky. 6% per year seems pretty high to me, but it just depends, what you're investing in, how it works out for you. But it's not totally unrealistic for retirement accounts. And you can kind of see here, for retirement, you have $250,000 more than if you didn't invest at all. And investing $2,000 a year into an IRA account isn't that much, especially after, when you graduate and you're paying off student loans and stuff. You have to prioritize certain things, but once you have all that paid off, you can do the maximum, which at this point, I know it's $6,000 a year. So you could triple that amount of interest if you did the maximum and got 6% per year. Almost a free $1 million if that worked out for you. All right, now the next one is really just doing the future value twice and comparing two investments, but this is kind of how you would put it in a computer or something to figure it out. but to figure out which investment is better. Now, an investor is presented with a choice of two investments: an established clothing store and a new computer store. Each choice requires the same initial investment, and each produces a continuous income stream of 3% compounded continuously. So they both have the same initial investment. So we can neglect that. That's not really important. And each has the same continuous income stream rate. There's definitely a missing word here. Income stream interest. So R is 3% for both of the investments. And we'll need to change that to 0.03. The rate of flow of income from the clothing store is F of T equals 14,000. So this is the income stream for the clothing store. And then the rate of flow of income stream for the computer store is expected to be, so this is new, which is why it's, it says expected, but that's what we have to go off. G of T equals 12,000 e to the 0.05 T. And the question is, which one would be the better investment over the next 7 years by comparing their future values? Right, so it's not going to be a multiple choice question where you just pick one or the other. You have to figure out each future value and then go from there. But the capital T in our formula is 7. I'm going to write down the formula again like I did last time. So we've got e to the r capital T, integrate from 0 to t, times, and then we integrate f of t. This is the continuous income stream, or the rate of flow of income. So for the clothing store, we'll use the 14,000. For the computer store, we'll use the 12,000 e to the 0.05 t, and then e to the negative r lowercase t dt. Right, but what we are basically doing the problem we did previously twice. Now that we have that formula, when we integrate the e part, it'll be a lot quicker though. All right, so I'm going to do the clothing store first. R for both, and T for both is 7. The only thing that's going to be different is the continuous income stream in the problem. So the clothing store, we have e to the 0.03 times 7, integrate from 0 to 7. Our f of t for the clothing store is 14,000 e to the negative r 0.03 t power dt. Right, now I'm just going to simplify like last time. 0.03 times 7 is 21, 0.21. We can bring the 14,000 out. Integrate from 0 to 7, e to the negative 0.03 t dt. And because I derived that formula in the last problem, I'm going to use it again. I know I'm not going to do the chain rule, or not the chain rule, I keep saying chain rule. I'm not going to do substitution to integrate this every single time. I'm going to use the formula in previous problem because it's the same type of integral. Right, so out front, we have, I'm going to rearrange to put the 14,000 out front, e to the 0.21. And then when we integrate e to the negative 0.03 t, we get itself divided by negative 0.03, the number. Now I will mention a very specific this formula, if you had t squared, it wouldn't work. So it has to be a number times t. But that's what we've got in this section. So that's why it's so useful. Then we evaluate from 0 to 7. Now it's up to you if you want to simplify like I did last time to make it a little easier to type in your calculator. I'm going to do the one step to simplify, which is simplify the numbers. So 14,000 divided by negative 0.03, math fraction, and it doesn't even change it to a fraction for me, even though it should. I'm just going to leave it alone then. I don't know why it didn't change it to a fraction for me. So I'm just going to move the negative up top and the 0.03 with that. But now I will evaluate. All right, so I'm going to plug in 7, subtract, and plug in 0. If I plug in, well, actually, let me just do the step out. And it looks like that. And then if I plug in 0, we got minus our negative 14,000. Once again, remember the minus is part of the integral part. This negative in front we cannot forget. Over 0.03 e to the 0.21 times e to the negative 0.03 times 0. And now I'm going to use my calculator. All right, so we've got negative 14,000 divided by 0.03 times e raised to the 0.21 times e raised to the negative 0.21. We multiply that out and we get that number. Once again, we'll get that number because the exponents here will cancel out, and multiplying these two would just be 1. So we got negative 466,666.667 minus minus, we know this will become a plus, and then type the second one in. If you pay close attention here, what's the only difference with the second one? Well, I changed the minus minus to a plus, so don't have the minus out front anymore. But the exponent here is just 0. And e to 0 is 1, so you can actually just get rid of the last thing. We got 575716.428. And then if we do our last remaining arithmetic step, take this number here and subtract off what we got above. We get $109,049.76. So this is going to be the future value of the clothing store in 7 years, the investment into the clothing store. Okay, now the computer store, we have to do pretty much the same thing, but our function inside is a little different. Because it's not just a number, it looks a little scarier, but if you do a simple exponent rule, which we'll see, it's really not too bad. So the future value of the clothing store, computer store I mean, we have the same E, or same R, E is always same, R is 0.03, T is 7, we integrate from 0 to 7, f of t this time we use our computer store formula, which is 12,000 e to the 0.05 t times e to the negative rt, e to the negative 0.03 t dt. And we go through and simplify and do the same thing. Right, now we can still do the same two things to simplify the first step as before. I can bring the 12,000 out, I can multiply the exponents. So I got 12,000 e to the 0.21, what those multiply to, integrate from 0 to 7, and on the inside I have 2e parts left. Now if you know how to go from here, there's one thing you need to do to simplify this, and then it's the same problem, just with a different exponent. What you need to do, and this is a requirement, is combine these into one exponent. Since they are being multiplied here, we add the exponents. That's our exponent rule. Right, so if you have e to the x times e to the y, it's e to the x plus y. So we add the exponents, right? And I guess I brushed over this, but the reason we cannot factor this e to the 0.05t out is because we have a t, a lowercase t with it. So it's got to stay inside. You go ahead and write that down actually. We can only bring things out of the integral if it's just a number, if it doesn't have the variable, in this case t. All right, so out front we got the 12,000 e to 0.21. We're integrating from 0 to 7. Now if you add those two exponents, you get 0.05t plus negative 0.03t, which would be 0.02t. They combine them into one exponent like that. And then we can integrate using the rule that I used over here and in the previous problem. But once again, if you would rather practice substitution and do substitution every time, you can do that. We got 12,000 e to 0.21t. Then when we integrate e to the 0.02t, we get itself back, divide by the number 0.02. Evaluate from 3 to 7. Now, even though I got bitten on it last time, let's see, does this simplify the numbers here? 12,000 divided by 0.02, that should simplify, and it does come to 600,000. So I am going to actually do that. Then we got e to the 0.21t times e to the 0.02t, evaluated from 0 to 7. We do our evaluation here. Plug in 7. We got 600,000, e to the 0.21, then e to the 0.02 times 7 minus 600,000, e to the 0.21 times e to the 0.02 times 0. And then we can evaluate. All right, so I'm going to do the thing in front. 600,000 times e raised to the 0.21 times e 0.02 times 7 is 0.14. We get $851,440.53. Minus, and then if we plug in the second thing, just hit second enter, the second exponent, yeah, everything is the same like before. And then the second exponent is 0, e to 0 is 1, so like the other ones I can just get rid of it. We got $740,206, and I forgot to look at the change, 84 cents. Then do our subtraction here. 851, 440.53 minus 740, 206.84. And we get $111,223.69. $233.69. And this is the future value of the investment in the computer store. Which one's larger? We can see that the computer store would be the better investment. Now, if you change the time parameters, this could change the investment strategies. So if you went with less time, the F of t would be better because the 14,000 invested, or the income rather, is more than the one on the bottom when it's low, when the t is short because it starts at 12,000. But what this e to the 0.05 t is doing is making the income stream grow over time. So if this went on, let's say if you had to compute it over 20 years, this second one would be so much higher that you would not even know why. You would ask the question, why would I invest in the first one? But because the initial amount of the clothing store is higher than the computer store, you kind of see that 14,000 and think that that might be the better choice every time. But if it goes on long enough and we see t equals 7 is long enough, the computer store will become the better investment. All right, but that is section 6.2, what we're going to be doing out of it. And kind of the culmination of this course, but I think that these questions are actually realistic type of questions that you would actually answer for investment type of problems. So pretty interesting to me.